So, as promised, we're going to look at something called addition polymers now. Addition polymers. Just to get you all excited about that topic, I've underlined this in a slightly different colour. I know you can barely contain yourselves, but do try. And addition polymers are called addition polymers because they're formed from the addition of more than one molecule. So if, for example, I have two molecules here of butene, and I add them together, I can be left with this molecule. And this, if I just show you this kind of sort of pseudo-mechanistically, you can imagine this attacking this, this picking up a hydrogen, and then ignore the fact that the charges aren't quite balanced. But that's the sort of reaction that you get. In reality, it's more likely to be a free radical mechanism. But if I then say, well, okay, instead of just having two of these, let's say I've got a lot of them, which I'll call N. Then I could carry on this chain that I've got, here. I could carry on just making that chain. So I've got here my one but molecule, and it's it's joined, to another but molecule, which joins another but molecule, which joins to another but molecule. Of course, in reality, these dotted lines that I've shown here to show you that they're separate molecules, they're not actually like that. They are just full covalent bonds. So I'll just draw them in turquoise for now, but they are just the same as the white bonds. And so this continues just for as long as the reaction allows it to, until it's terminated. So we can draw this with an arrow around it, a bracket around it here, and put N, or maybe it's M because we've always used N. And that means that this is going to be a repeating unit. But when we draw repeating units, what we should actually do is we should try and get them into the simplest form that we can. So really, we shouldn't be drawing it like this, but we should instead be drawing it like this. And this is the simplest form of this repeating unit, like that. So from this repeating unit, you can work out backwards, you can work out what the monomer is, which is butene, which is what we started with. So I've given you a lot of information there, so let's just slow down and go back a bit and look at some of it. So the first thing is that this is called a monomer. Mono meaning one, and the result from that, for example, this is called a polymer. Poly meaning many. So you start with a monomer, a one-off, and you make a polymer, a many of. And this is addition polymerization, to go from here to here. And I'm just going to put ADDN as a shorthand for addition. Addition polymerization. As I said, this is often a free radical mechanism, but you don't need to worry about the mechanism for now. Often a free radical mechanism. And if you look at some of my additional content lectures, I've talked a little bit more about that there. So now that we've kind of looked at that in a very overview way, let's just scroll back a bit and have a look at that again, to hopefully make it a little bit clearer. So we make addition polymers. Addition polymers are made from monomers. Monomers for addition polymers in this case have a double bond, a carbon-carbon double bond. That double bond forms the polymer linkages, or chain. Polymer linkages. So to give you an example of what I'm talking about here, let's start with this molecule, which is called chloroethene, also known as vinyl chloride. Or let's give it its full name, which is its EUPAC name, which is chloroethene. And let's polymerize this. So let's say we're going to do it with a free radical mechanism, so we're going to use light, and we're going to end up with this sort of mechanism, this sort of molecule. And so on and so forth. So if I were to draw, instead of drawing this out as a full molecule, which would take a long time and be very boring, instead I'm going to draw it as a repeating unit. So I've got this, and then I've got, I beg your pardon, let me start this again. Let's say I've got, that's my central unit, and then I've got my two linkages here and here, and that's my repeating unit. And you might recognize the name of this already, kind of giving it away a little bit, but when we're naming monomers, it's very simple. We just take the name of the monomer. When we're naming polymers, we just take the name of the monomer and we just write a poly before it. So poly, and then we take this name and we put it over here. And so that's why this is called polyvinyl chloride, or polychloroethene. And that is shortened to something which you might have heard before, which is PVC. And PVC is used to make things like window frames and doors. And one of the benefits of addition polymers is that they are relatively unreactive. They are relatively unreactive. And that's what allows PVC to sit out in the sun for a very long time, and it doesn't change colour, it doesn't react. There's a lot of energy going into it from the sun's rays, but because these are relatively unreactive, it doesn't really do much. That's one of the great benefits of them. Let's look at another example. Example 2. So let's take this molecule, which is propene. Let's polymerize this with UV light, and then let's go straight into drawing the repeating unit. That wasn't a great example of that. I might redraw that. So this was propene. So this is, remember how we name these? You take poly, and then you take the name, and you stick it over here. So this is polypropene, sometimes referred to as PP. And you might have heard of this referred to as well as polypropylene, and that's just because propylene is the old name for propene. So propene is sometimes called propylene. So polypropylene is PP, and that's used all over the place, kind of a clear, hard plastic, and you might have experienced that in your life, and now you know what to look out for. Sometimes on the bottom of things, they'll have the little, the sort of the recycling symbol, this symbol, and then sometimes in the middle they'll say PP, or PE sometimes. Sometimes it says PE, and PE is just polyethene or polythene, and so that would just be, if we just take that and we polymerize that, then your repeating unit would simply be, so this is polythene or polyethene. And this is what carrier bags in supermarkets are made out of. Carrier bags. Although they're being phased out now, instead you get bags for life. But before bags for life, we used to have carrier bags made of polythene or polyethene. And so it's quite a soft, quite stretchy plastic, and that makes it really good for bags and carrying heavy loads. So we know now that addition polymers are unreactive. We know how to name them. We simply take the name of the monomer, which is the starting molecule like this one, and we add poly to the front of it. We know that some common molecules that we use, some common polymers that we use all the time in our lives come from very simple monomers. So polythene for carrier bags comes from a really simple monomer, ethene. We know that polypropylene comes from propene, and we look at polyvinyl chloride, PVC, comes from vinyl chloride or chloroethene. And what is important to understand is that over time we've hugely developed our understanding of polymers and their properties. So polymers now are extremely complicated because they've had a whole host of additives added in that go beyond simply taking a monomer and polymerizing it. So polymer chemistry has gone way, way beyond these original simple polymers. And so when we say polythene or polypropylene, it's actually more complicated than that. There will be additives in there to change its properties. We'll be changing the chain slightly. We're putting in what are called copolymers in small amounts, and these can totally change the behavior of the polymer. But what you need to remember is just that the production and properties of polymer has developed over time a huge amount. So you need to know the typical uses of these plastics, which we discussed, and we also need to understand that when you have additives, these change the properties of the polymer. And the best one to remember that you might get asked a question about is called plasticizer. So it's got e.g. plasticizer. And as the name suggests, this makes the polymer a bit more plastic. It makes it a little bit less brittle. It makes it a little bit more floppy and malleable, and you can move it around more. So now let's have a look at some examples of questions you might be asked in the examination. And those questions typically take the form that you're asked to draw a unit given some information. So one example might be that you get asked to draw, so let's have question 1, and this might be draw the repeating unit of this monomer. And so you might be given some monomer, might look like this, might have some other complexity to it, doesn't matter. And you need to draw the repeating unit. So what you do is you take this double bond here, and you split that double bond out so that it comes out both from this side and from this side, and then you get rid of one of the double bonds, and that's what you're left with is then the repeating unit. So here I would have methyl, this, and then this. But you need to kind of orientate it so that you can get your brackets in, because if you remember, I need a bracket here, and I need a bracket here, and then I need to put my N, and that makes it quite difficult to draw. So instead of doing that, let's not do that. That looks horrible. It's a mess. Why would we do that? Instead, what we're going to do is we're going to have our central bond here, and then we're just going to go straight up here and put O-methyl here. We're going to go straight up here, and we're going to put C2H5, which is this group here. I'm outlining in green. That's 2 carbons and 5 hydrogens. That's an ethyl group. And then I'm going to just put my other bonds straight out here and straight out here, and then I can draw like this. And that's much neater. So you can do it like that. So this is the repeating unit of this monomer once we polymerize it. So that would be question 1. And question 2, it might be something like draw the repeating unit of this polymer. And so you might be given a polymer, and the polymer might look something like this. So on and so forth. Or it might have other complexity to it. And you need to be able to unwrap this, or work backwards, and to draw instead the repeating unit of it. So you need to find a point at which this starts to repeat. So for example, if I look here, where I put my orange line, and I start counting to the right and wait until it repeats. So I've got a carbon here, it's got a methyl hanging off it, then I get a carbon by itself, then a carbon with a methyl hanging off it, then a carbon by itself, then a carbon with a methyl hanging off it. Aha! And so if I go back a bit, where did this start to repeat? Well, actually it repeated all the way back here. So carbon with methyl, then carbon, carbon with methyl, then carbon. So the piece between my orange lines, that's my repeating unit. So if I were to draw this as a repeating unit, I would draw just the piece between the orange lines. I draw these two bonds, I put my brackets in, and then I put my N, and that's the repeating unit. And hopefully you recognize that this is, again, this is polypropene or polypropylene. So that's fairly straightforward. You just need to find where it repeats. You take that section, put brackets around the linking bonds, and then you put an N. And then you might have another question, which is if you're given the same section of polymer, you might be asked to draw the monomer instead. So let's just use exactly the same example. So I've got my polypropene here, and you've been asked to draw the monomer. Draw the monomer. So this means you're working backwards, you're saying what did this come from? And in this case we've already worked out the repeating unit, we've got that up here. So I can just use that repeating unit, that would be the first step, so you'd work out the repeating unit and then you simply put the double bond back in. So if I look up here at my repeating unit, wherever there is a linking bond, so here and here, you fold those back in and make a single bond from them. So you'd end up with a bond here. And you'd remove the linking ones, and you're left with the monomer. So let me get rid of some of the mess from that. So I would be left with simply that. And this, of course, is propene, and this is the monomer of the above polymer. If you prefer to draw this non-scalically, this is the structural formula. So you could draw it like that instead if you'd rather. And in all of these cases you can draw these either, unless it specifies you can draw them out fully, or you can use the skeletal formula. But I'd encourage you to get used to using the skeletal formula. It's far more used in industry, it's what chemists use in day-to-day work, and it's kind of widely accepted as the standard really for drawing chemical molecules. You then might be asked some additional questions about why these molecules are unreactive, and the answer to that is that they are unreactive because they have a lack of functional groups with which to do chemistry. So there's nowhere really for things to bind in. Alkanes typically are fairly unreactive, and that's basically what we're making. We're making long chain alkanes with possibly some functionality on it, but by and large alkanes are unreactive, and therefore so are these monomers. Really the only way of doing much with them is by combustion, burning them, or with pretty aggressive chemistry. So extremely strong acids, for example, might react with them. But by and large, these are unreactive due to a lack of functional groups and the strength of the carbon-carbon bond. And then finally, the last piece to talk about this is to talk about these not just by themselves. So if I have, for example, polypropene here, and this carries on into the distance, into the sunset. And what happens if I have another molecule of polypropene sitting next to it? How do these interact? Well, the answer to this lies in something called van der Waals bonds, van der Waals forces. And what happens is that if you imagine that this molecule has an extended electron cloud, because all of its bonds have got electrons in them. So this molecule can be kind of considered to be a big electron blob, and there's electrons here in all these bonds, around all the hydrogen bonds as well. And this molecule also has an electron cloud around it. So there's a big blob of electrons on both of these. And this electron cloud is not static. Electron clouds are moving all the time. So as the electrons are moving within these clouds, you end up with local areas of negativity and positivity. To give you an example of that, let me just draw you one area of electrons. And this is hugely oversimplified, by the way. This is not the reality of the situation, but let's say I have an electron here, an electron here, an electron here, an electron here, and let's say these are all moving around randomly. Now, because the movement is random, there's a chance that, for example, as I've drawn here, if I just progress this a little bit in time and draw it in orange, where would these molecules be at that point in time? Well, this one, number 1, might be over here. This one, number 2, might be over here. This one, number 3, might be over here. And this one, number 4, might be over here. So if I now remove... So I'm going to remove the green electrons from the original positions. I'll just be left with the orange electrons, which is where they've ended up after some period of time of them moving randomly around. And you can see from this, hopefully, that the electron density on the left is higher than the electron density on the right. And that means we'll end up with a slightly negative side and a slightly positive side. So I've drawn this as delta positive, delta negative, which means a little bit of negative and a little bit of positive. And over time this could flip, so I could end up with delta positive on the left, delta negative on the right. I could end up with delta negative at the top and delta positive at the bottom. So I could have all of those arrangements, and these are constantly changing all the time. And this is called a temporary dipole. So a dipole, funny word, but it means there are two poles. So if you think of this as a magnet, then this end is the positive pole, this end is the negative pole. And so we have a dipole, but it's temporary because it might just flip, because the movement of the electrons is random. So electron movement is random. So this statement is important to remember when we're talking about van der Waals forces. So these are van der Waals forces. And you might be wondering, why on earth is he going on about this? How is this relevant at all to polymers? Well, if we look at the two molecules that we have on the left, the two molecules of polypropene, these big electron clouds that I've drawn in orange and in red both constantly set up these temporary dipoles. So you end up with, all the time you have little delta negatives, little delta pluses, little delta negatives, little delta pluses. And the same on the other one. So you end up with these sorts of arrangements. And what happens is, let me delete them from the second molecule, what happens is, as the molecules approach one another, let's imagine for a moment that the red molecule had no temporary dipole in it. Just for a moment, all the electrons were perfectly spread out. As the orange molecule approached it, each of these charges would start to affect the red molecule. So this charge here, this will start to make this area slightly positive as it pushes the electrons away, because these electrons are negative, so they will push the electrons slightly away from this area and make it delta positive. And similarly here, a delta positive area will make this delta negative as it pulls the electrons in to compensate, and so on and so forth. This is called induced dipoles. And this results in a bonding effect. It's a weak bond. It's not as strong as a covalent bond. It's certainly not as strong as an ionic bond. But this is still a bond. This is still an attractive force between them. So this attractive force is felt between the two dipoles, because on the one half I have delta positive, and the other half I have, on the one half I have delta negative, and on the other half I have delta positive. And positive and negative attract. And same thing here. I have positive and I have negative. I have positive and I have negative. And these will always attract one another because opposites attract. And this bonding is referred to as van der Waals bonding, or temporary induced dipoles. And the outcome of this is that if I have a longer chain polymer, that can have a stronger van der Waals bond between two polymers than if I have a short chain polymer. Because if you imagine in the second case, the amount of space I have to bond these two together is simply this, in the orange, whereas in the top molecule, the space I have to bond these together is all of this space. So in the first example, the bonding is stronger because there are more dipoles and bigger dipoles that can be set up, and in the second one, bonding is weaker. And this relates directly to things like boiling points and melting points. So the top molecule will have, for example, a higher melting point. So it might be like a wax. And the lower molecule will have a lower melting point. So it might be, for example, an oil. And this all arises because of the size of these van der Waals forces between the molecules. So this was a run through of addition polymers and some example questions. So we've gone through here some examples you might be asked. So drawing repeating units from monomers, drawing repeating units from the polymer, draw the monomer from the polymer. So they're fairly straightforward and similar questions. You just need to make sure you understand what they're asking. So you need to get your terminology correct. So for example, if you need to understand what a monomer is, a monomer, oh, beg your pardon, monomer, this is the single unit, e.g. you need to understand the polymer is the multiple unit, e.g. and you need to understand the repeating unit, e.g. And if you can understand those terminologies and know what each of them is, then these questions should be pretty straightforward. Beyond that, it's simply working out where the molecule starts to repeat, splitting that out, and either converting it into the monomer or into the repeating unit. So in the next lesson, we're going to start looking at alcohols, which is a totally new functional group. So that's going to be exciting. So we're going to start looking at alcohols, and that's where the functional group is an oxygen and a hydrogen. So we've got some carbon chain, and then at the end we have an oxygen and a hydrogen, and this is the alcohol functional group. And this includes obviously the best known alcohol, which is ethanol, which is the one that we drink. But it's also got a whole host of other ones, such as methanol, butanol, and lots of others. So that's going to be the content for the next lesson.